Good afternoon, everyone. I'm Phong from the School of Data Science, University of Virginia. Today, I would like to present to you one application of artificial intelligence, typically deep learning in modeling the structure, property, performance linkage of fresh energetic materials under shock loading. Typically, in this case, we use a physics-aware recurrent convolution neural network, or in short, PARC. So let's get started. Firstly, why do we want to study that complex physics of energetic material? So generally, energetic material is a key component in many applications, both military and civilian. In energetic material, we care about the sensitivity of the material. In short, how easy it will release the storage energy, and moreover, from years of researching about EM, one thing we know is that the microstructure of energetic materials highly affects the sensitivity of the materials. So the idea is that by controlling the microstructure, you can control the properties of the materials and can eventually converge into a design with enhanced performance. So that is a problem that we can solve with a material design process. However, within this process, we have to iteratively generate material samples and assess its properties before making decisions. And this analysis process is extremely laborious and costly, and it's really become the bottleneck of the whole framework. So in our case study, as you can see in here, numerical simulation is used, but it can cost like days on high performance computing cluster, and it is both too time consuming and too expensive as we have to analyze a vast configuration space. So that is actually where machine learning comes in, because machine learning can provide accurate predictions after well trained, which like much shorter period of time. So for example, the simulation instance that you are seeing right now on the bottom for DNS or direct numerical simulation, it costs more than a day on our collaborative facilities. While the machine learning model can provide relatively similar result or with less than a second on my personal laptop. So how do we achieve that capability? The thermodynamics, the thermomechanics of energetic material, which shock applied, can be considered as a dynamical problem and can be formulated with the governing equation as shown in here. We also have the initial condition. Here we care about the derivation of temperature and pressure field within the microstructure during the shock applications. So, in general, at a given time tau, the quantity of interest, in this case, temperature and pressure, can be determined with this formulation. And because the dynamics here is so extreme, includes nonlinearity from both spatial and temporal domain, when the time tau increases, the solution becomes more and more complex, and generally it's nearly impossible to derive a stable numerical simulation. Because of this reason, a stepwise discrete time solution is usually used. So in this formulation, in a temporal domain discretized into finite step with equal time interval, the quantity of interest value at a given time step is determined using the values at the previous time step as shown in here. And the integration term, which denote the change of the quantity of interest over time, is a very complex function. And because of that, it can be modeled as a convolutional neural network. Moreover, instead of model the whole integration as a neural network, we follow a typical solution process of a normal direct numerical simulation, in which the governing equation describing the rate of change and its integration over time are modeled separately. And this mathematical formulation of the solution lead to the design of our deep learning architecture. So from a given microstructure and position field, a descriptor, carrying the information about the shape of the microstructure and the variation of the shape are extracted and serve as constant parameters in the model via a neural network. And from the initial condition, we first derive the time derivative of the quantity of interest, in this case, temperature and pressure field. Consequently, a data-driven integration is performed to compute the actual change of the quantity of interest, and the values is added to the quantity of interest initial condition to derive the values for the next time step. And the same process is repeated recurrently, until the final time step is reached. And note that the parameters of differentiator and the integrator are all shared between time steps, making the architecture recurrent. So for the training of this model, we only use 30 simulations. Only 30 training samples are required. So each training sample include a microstructure image acquired from micro CT scan and a series of 19 snapshots of temperature and pressure fields derived from direct numerical simulation, and the time interval between two consecutive snapshots is 0.79 nanoseconds. So what is the prediction accuracy with this small training data set? So here I present the temperature field predicted by the model in the second row with its corresponding ground truth derived from direct numerical simulation on the first row. And as you can see, all of the hotspot, which is the area with high local temperature, are well recognized, and as well as the shock fronts that enter the microstructure can also be clearly recognized. And for the pressure field, we can also recognize the same thing. And the shock fronts and the patterns in generally are well recognized. Further quantitatively evaluating the model, we can see that the sensitivity metrics predicted by the deep learning model here, including the hotspot temperature, the temperature area, which has the area with temperature that higher than 800 kelvins, considered as the hotspot area, and the average hotspot temperature, the average, and the total hotspot area, their derivative over time, they are all in agreement. They are all in agree with the ground truth derived from direct numerical simulation. So our model can predict the complex physics very well, but is the prediction trustable? So that's concern bring us to another advantage of the method, which is the interpretability of the deep learning model. And there are actually a few reasons for the requirement of an interpretable model, especially in this case when we are dealing with anisotropic material. Firstly, we need that interpretability in order to validate the trustworthiness of the prediction. Secondly, we needed to understand the correlation between the input and output, or knowing why the model making that decisions. And finally, it can potentially provide new and unknown information that we don't know. And the interpretability of the model can be achieved by the use of saliency map visualization. So generally, saliency map is a technique that allows us to know what area or features of the input of the image mostly affect the prediction. So it is computed by taking the derivative of the neural network output. So in this case, the temperature field with respect to the input. So in this case, the microstructure intensity field. The derived saliency map is then registered to the microstructure image for better visualized and identification on which area that microstructure is critical for the hotspot formation. And interestingly, we found that the CNC map highlight all of the area that belong to void and cracks, which agree with the literature that cracks and void are the potential area for energy localizations, which lead to the formation of hotspot. And from this visualization and identification, we actually can go one step further by cropping the critical microstructure area and compare it with the non-critical one. And we actually do that by cropping and perform shape analysis. And interestingly, the analysts show that the analyst is also agrees with the previous finding in the energetic material, such as the direction of the void is more important than the aspect ratio of the voids. And also from the analysis result, we can also identify the type of voice with these morphometry characteristic can lead to the energy localization and form the hotspot. And this result on the orientation that I present here indeed agrees with the previous finding in the EM literature, and thus it's provide the validity for our deep learning model. So in conclusion, our deep learning model can drastically reduce the computation time from hours and days on a supercomputer into less than a second on personal laptop. Secondly, it can provide a accurate prediction result, and also the prediction is interpretable, proving the trustworthy of the model. And finally, with all of this, it can be used in a design optimization to explore for the better material. And potentially, we are thinking about two applications of our model. One is using it in a microstructure inverse design, in which the user gives the target property and the AI will perform the design optimization, and eventually we can converge into the microstructure design, which gives us the desired properties. And the model can also be useful in non-destructive quality control, in which we can just take a micro CT image of the as-built microstructure and send it into the deep learning model for rapid properties estimation. So in the future, we are planning to enhance the prediction accuracy by some method, and also quantify the uncertainty that caused by the lack of training data in the model. And finally, still, the small scale data is a serious problem that we need to face. That will form all of the future work that we are planning to do. And that will also conclude my talk. And thank you for your attention.